All right, ICE tables, folks. ICE is an acronym. It stands for Initial Concentration, Change in Concentration, and Equilibrium Concentration. We'll get into that in a moment. Um, uh, we are not going to work a full ICE table problem here for about 15 minutes. We are going to talk about the concepts. We are going to introduce this idea of reaction quotient that allows us to predict what direction an equilibrium will go to reach equilibrium, or what direction a reaction will go to reach equilibrium, all that beautiful stuff. So here's what we got. Okay, conceptually, we're just going to talk about this reaction. Let's imagine we have this synthesis reaction here. Okay. A ICE table problem would look like this. It would say, what will the equilibrium concentrations of everything be if we start with this much carbon monoxide? Notice this little zero down here. That little zero means initial or starting concentration, not equilibrium. So if we start with this much CO and we start with this much H2, and if the reaction has an equilibrium constant of 26. So just notice we are not going to solve this problem. In fact, this problem would require us to do a trinomial. It's higher than a second order polynomial, so we are not going to get into this. Okay, we could solve it with the x is small assumption, but you can't do that with this one. Anyway, getting ahead of myself. Let's start and talk about this. This problem is easy to predict what direction the reaction has to go to reach equilibrium. Here's why. We don't have any product in there to start with. We essentially have taken a container, we've pumped in the reactants, and we didn't pump in any product. So since there is no product, the reaction cannot possibly go from right to left. We don't have any product to rip apart. No matter what the equilibrium constant is, and it actually turns out that this reaction slightly favors the product side. But regardless of what the equilibrium constant is, if I don't have any product, this reaction has got to go to the right to reach equilibrium. So what's going to happen? Well, the amount of the reactants is going to go down, right? The carbon monoxide amount is going to go down by some amount, x. Okay, and it's a 1x because it's got a 1 out in front of here. So let's go down by some amount, let's say 1x. And the amount of hydrogen is going to go down by twice that amount. We'll call that 2x. So in order for this reaction to reach equilibrium, this is going to get consumed. This is going to get consumed at twice the rate of that. And we're going to make this product. And that's going to go up by a factor of 1x because this has also got a coefficient of 1. So the amount that this goes down, that's the same amount that this is going to go up. Okay, so hopefully you can see how this problem is different. I'm going to teach you how to set up ICE tables to kind of keep this organized and everything. But hopefully you can see we're starting with initial concentrations. And when you start with initial concentrations, you are in for a much longer problem. Okay, because these are not the equilibrium concentrations, I've got to do a way more work. Okay, now, sometimes it is not as obvious to predict what direction a reaction needs to go to reach equilibrium. Now, this time is very easy. It is always very easy to predict what direction the reaction must go to reach equilibrium if you are missing something. Because if you are missing something, it must go towards what is missing, right? If something is missing, then you cannot go in that opposite direction of what is missing because there's nothing to react in that direction. Let's say, for example, let's say I had some of this and I had some of this, but I had no hydrogen in the flask to begin with. Well, now, since I'm missing hydrogen, it's got to go towards the reactant side because if I don't have any of this, it can't go to the right. It would have to go left to reach equilibrium. It is always easy to predict what direction a reaction will go to reach equilibrium if you are missing something. If you are missing something, you do not have to do this next thing called the reaction quotient. If you have an initial concentration of everything, then how do you know what direction the reaction has to go to reach equilibrium? Well, the answer is if you have an initial concentration of everything, then you have to calculate what is called a reaction quotient. The reaction quotient is abbreviated with a capital letter Q. And the reaction quotient is found very simply. It sounds complicated. It's very simple. The reaction quotient is found by plugging the initial concentrations into the mass action expression and solving for, normally, if I plugged equilibrium concentrations in, I would be solving for the equilibrium constant. But if I plug initial concentrations in, now I'm solving for the reaction quotient. So, for example, let's do this bad boy right here. So we got this reaction, two NOs and a Cl2 react to make two NOCls. We got a 2-liter flask, and in that 2-liter flask, we're gonna pump in this many moles of NO, this many moles of Cl2, and this many moles of NOCl. And the first thing I want to do is predict what direction the reaction needs to go to reach equilibrium if it is not at equilibrium. So here's what we got to do. The first thing we need to do is write a mass action expression. So I want you to write a mass action expression here in a moment. Then what I want you to do is I want you to turn these into concentrations. So remember, it's got to be molarity, right? These are only moles. So you got to divide each of these guys by the volume of the container to turn them into concentrations. These are going to be the starting amounts of these things. So since they're the starting amounts, we're not actually solving for the equilibrium constant anymore. We call it the reaction quotient. Now, if you plug these values into the mass action expression and you get 65,000, then you must be at equilibrium because you got the equilibrium constant. But if you plug these values in and you get a number that is not 65,000, then you are not at equilibrium and the reaction is going to have to shift, and we'll talk about how you can predict it. So a couple things here, many steps. I need a mass action expression for the reaction. I need you to divide each of these by the volume of the container to turn it into moles per liter to get the concentration. I then need you to plug those values into the mass action expression, and I want you to solve for the reaction quotient. Go ahead and do that, and we'll meet up once you have that answer, and we'll talk. All right, here we go. So we are not plugging equilibrium values in, we're plugging initial values in, which means that's not an equilibrium constant anymore, it's a reaction quotient. So let's plug it in and calculate, see where we're at. So that's going to be 3.4. Oh my goodness, I almost forgot to square that. That would have been bad. Divided by, where are we at here? 0.010 squared times 0.0042. Oh my goodness, and I got a big old number. What do we got? 1, 2, 3, 4, 5, 6, 7. I got 2.8 times 10 to the 7th, I believe, or 28 million. 1, 2, 3, 4, 5, 6, 7. 2.8 times 10 to the 7th. How many people got 2.8 times 10 to the 7th? Give me a thumbs up. Oh, yeah, there's some thumbs up. 2, 3. Okay, good. So we can't all be wrong. Here's the first question. This reaction cannot possibly be at equilibrium. Okay, here's why. If it was at equilibrium, we would get the equilibrium constant. And I told you in the problem that the equilibrium constant was 6.5 times 10 to the 4th, which is 65,000. We don't have 65,000. We got 28 million. So when I plug these values in to the mass action expression, I do not get the equilibrium constant. I get a number that is bigger than the equilibrium constant. Okay, so there are 3 scenarios that can occur when you plug initial concentrations into a mass action expression and compare them to the equilibrium constant. The first scenario is that you plug those values in and they could equal the equilibrium constant. So that's like scenario 1. If that happens, which is never going to happen, you're done because the reaction is already at equilibrium. That would mean it's at equilibrium. That is never going to happen. One of these other 2 things are going to be what's going to happen to you when you're doing these problems. Let's talk about the scenario that just arose. We have a number that is bigger than the equilibrium constant. So we have Q is greater than Kc. What does that mean? I promise you that I have been doing this for 15 years, and I have been taking chemistry now. I have been doing ice tables and stuff now for almost 20 years. No, more than that. Good Lord. How old am I? More than 20 years. 22 years I've been doing chemistry. like learning this stuff. And I refuse to memorize this. I stop and think about it every single time. Now, some people prefer to memorize what I am about to talk about. That's up to you, right? I got enough things in my brain. I can't squeeze something I don't need to memorize in there. Here's why I don't memorize what I'm about to tell you. I stop and think about this every single time. At the end of the day, these mass action expressions are product concentrations over reactant concentrations. And if I have a number that is too big right now, when I plug this junk into the mass action expression, I got a number that's bigger than where I need to be at equilibrium. If that happens, well, what must be true? How do you have a number that's bigger than another? Well, my numerator must be too big, and my denominator must not be big enough. So in order for this reaction to go from 28 million and reach equilibrium, where when the numbers get plugged in, they give you 65,000, I need less numerator, more denominator. Well, I need less product, more reactant. That's going to be a leftward shift. If you calculate a reaction quotient and your number ends up bigger than the equilibrium constant, then the reaction needs to go left to reach equilibrium. This reaction, this would actually go down by some amount, 2x. This would go up by x, and this would go down by 2x. We have got to consume this and grow these in order to bring this number down, right, and get closer to 65,000. So that's a shift left. The opposite is also going to be true. Let's say I had plugged these values in and I got a really small reaction quotient. Let's say I got 2.8 times 10 to the negative 7. Well, now that number is less than 65,000. So how do you get a number that's too small? Well, my denominator would be too big and my numerator would be too small. So I would need to shrink this, grow that. That would be a rightward shift. So if you end up with a scenario where the reaction quotient is less than the constant, you got to go right. You got to shift right to reach equilibrium. So I want you to understand what you got to do here. If you are missing some, if you're given initial concentrations and you are missing something, that is the greatest thing ever because you don't have to do any of this crap. You just know right away the reaction shifts towards what's missing. But if you are given initial concentrations and you have a little bit of everything, then you got to go through all this work. You got to plug those initial concentrations into the mass action expression, and you got to compare the reaction quotient you get to the equilibrium constant. If the reaction quotient is greater than the equilibrium constant, you're going to go left. You're going to consume products, make reactants. And if your reaction quotient is less than the equilibrium constant, you're going to go right. You're going to consume reactants and grow, make product to try to bring that number back up. So yeah, this is just the start of these. We didn't even get to ice tables yet. So hopefully here in that reaction you saw we had equilibrium constant that was way greater than the, we had a reaction quotient that was way greater than the equilibrium constant. That reaction shifted left to reach equilibrium. Here you go, same thing, different story. If they're equal, reaction is at equilibrium, no shift. If the reaction quotient is greater than Kc, shift in left. If the reaction quotient is less than Kc, shift in right.